Hey there, welcome back. My name is Liam, and this is Deep Space Intelligence, the channel where we take the biggest and most unsettling questions that physics hands us and follow them wherever they lead, no matter how strange the destination turns out to be. If this is your first time here, then I'm genuinely glad you found us. And if you have been with us for a while, then you already know that we do not deal in easy answers or comfortable reassurances on this channel. We deal in the truth as science currently understands it, and sometimes that truth is profoundly, quietly disturbing. Today, we're going to talk about something that has been rattling around inside my head for a long time, something that I think about when I look at a burning candle, or when I watch smoke curl up from a fire, or when I stand at a window on a cold night and breathe out a cloud of vapor into the dark air. I think about what is actually happening to all of that. Where does it go? And the answer that physics gives us is not what most people expect. Because according to our deepest and most rigorously tested laws of nature, nothing truly disappears. Not a flame, not a thought, not a person, not even a star collapsing into the most destructive object in the known universe. Everything that has ever existed leaves a mark, encodes itself into the fabric of reality, and in some sense that our mathematics can describe but our intuition struggles to hold, it never fully stops existing. And that should disturb you. Not because it is terrifying in a dramatic sense, but because it quietly dismantles the way most of us think about endings, about loss, about destruction, and about what it means for something to be gone. Let us start from the ground up, because this story begins not with black holes or quantum mechanics, but with a campfire. Think about that for a moment. A log of wood sitting on a pile of kindling. Before you strike the match, that log is a specific, definite object. It has a measurable mass. It has a chemical composition, long chains of cellulose and lignin, water locked inside the fibers, trace minerals absorbed from the soil where the tree once stood. It has a history encoded in its rings. It has, in a very real and precise scientific sense, a specific identity described by the arrangement of every atom inside it. Now, you light the match. The fire takes hold. Over the next hour or two, that log seems to simply cease to exist. The wood shrinks, blackens, crumbles, and eventually all that remains is a small pile of grey ash, a fraction of the original mass. The rest, to the naked eye and to casual intuition, is gone, vanished into the air, into nothing. But that is not what happened. Not even close. The carbon atoms that made up the wood combined with oxygen molecules from the surrounding air and became carbon dioxide gas rising invisibly into the atmosphere. The hydrogen atoms bonded with oxygen to form water vapour, which dispersed into the surrounding environment. The energy locked inside the chemical bonds of the wood, energy that had been stored there since the tree pulled carbon dioxide out of the air and used sunlight to build those molecules, was released as heat and light, radiating outward in every direction, ultimately dispersing across the room, then through the walls, then into the broader thermal environment of the building and the neighbourhood and eventually the planet. Every single atom that was in that log is still somewhere. Every single quantum of energy that was stored in those bonds has simply transformed and spread. Nothing was created from nothing. Nothing was destroyed into nothing. The universe, obeying the first law of thermodynamics with the same relentless mathematical precision it always does, simply moved things around. This is the law of conservation of energy, and it is one of the oldest, most deeply verified and most important principles in all of science. Energy cannot be created from nothing. Energy cannot be destroyed into nothing. It can transform from one form to another, from chemical to thermal to electromagnetic and back again, but the total amount of energy in a closed system never changes. When you add the mass of the carbon dioxide and water vapour and all the other gases produced by the fire together with the ash, and you account properly for the energy radiated away as heat and light, and you factor in the fact that mass and energy are interchangeable through Einstein's famous relationship, then you find that the books balance perfectly. Everything that went in is still there, accounted for, conserved. The universe, it turns out, is a perfect accountant. But here is where the story starts to get richer and stranger, because that principle of conservation, of nothing truly being destroyed, runs even deeper than thermodynamics. It runs all the way down into the quantum mechanical foundations of reality, and there it takes on a much more philosophically loaded and genuinely eerie character. In quantum mechanics, the state of any physical system is described by something called a wave function. This mathematical object encodes everything there is to know about a particle or a system of particles. It tells you the probabilities of finding a particle in different positions, the probabilities of it having different momenta, different energies, different spins. It is, in a very precise technical sense, the complete description of the physical reality of that system. Now, quantum mechanics tells us that wave functions evolve over time according to the Schrödinger equation, and this evolution has a very important property. It is unitary. That is the technical term, and it is crucial. Unitary evolution means that the mathematical transformation that takes a wave function from one moment in time to the next is perfectly reversible. There is no information loss built into the process. If you know the complete wave function of a system at any given moment, the laws of quantum mechanics allow you to run time forward and predict the future state with perfect precision, or to run time backward and recover the exact initial state from which it came. The physicist Leonard Susskind, one of the giants of modern theoretical physics, has put this in stark and memorable terms. The principle means that the universe is, in a deep fundamental sense, reversible. Every quantum event, every interaction between particles, every transformation of energy and matter preserves the total information of the system. Nothing is ever truly lost. The past is in principle always recoverable from the present state of the universe, if only you could read that state with sufficient precision. This is not a minor technical footnote. This is a cornerstone of quantum theory. Physicists call it unitarity, and it is so fundamental that the entire mathematical framework of quantum mechanics depends on it. If unitarity were violated, if information were genuinely destroyed in some physical process, it would not just be a puzzle or an anomaly. It would be a catastrophe for physics as we know it. It would mean that the laws of quantum mechanics, the most precisely tested theory in human history, are fundamentally wrong. So when physicists talk about conservation in physics, they're talking about something much deeper than just energy. They're talking about information itself. Every physical state of the universe carries a specific, complete, irreducible description, and according to our best understanding of quantum mechanics, that description can never be erased. It can be scrambled beyond any practical hope of recovery. It can be dispersed across vast regions of space-time in forms so diluted and entangled that no conceivable experiment could ever reconstruct the original. But it cannot be destroyed. Not truly. Not completely. Think about what that means. Every book that has ever burned carries, in the arrangement of the smoke molecules and the heat radiation and the chemical reactions in the surrounding air, a scrambled but theoretically complete record of its contents. Every conversation ever spoken and then forgotten has left traces in the pattern of molecular vibrations propagated outward into the environment. Every human being who has ever lived, every thought they ever had, every cell in their body, all of it dispersed at death into a vast cloud of atoms and energy, but none of it truly gone. Physics says that the information, the complete quantum description of everything that happened, is still out there, encoded in the correlations between particles, in the subtle statistical signatures of radiation, in the residual structure of space-time itself. This idea has a name among physicists. It is sometimes called the conservation of information, and it is one of the deepest and most contested ideas in all of theoretical physics. It sits at the intersection of three towering frameworks: quantum mechanics, general relativity, and thermodynamics, and the friction between those frameworks when it comes to information conservation is where some of the most profound mysteries in modern science live. And the most dramatic, the most spectacular, and the most philosophically vertiginous place where those mysteries converge is the black hole. Let us talk about black holes. Because if anything in the universe seems designed to destroy information, to genuinely annihilate things into nothingness, it is a black hole. They are the universe's most extreme objects, regions where gravity has overwhelmed every other force, where matter has been compressed so severely that space-time itself curves to the point of no return, where even light, travelling at nearly 300,000 kilometers per second, cannot achieve escape velocity. The event horizon of a black hole is the ultimate boundary, the point beyond which nothing we can ever observe or interact with again can escape. When a massive star runs out of nuclear fuel, the outward pressure that has counterbalanced the inward pull of gravity throughout the star's life suddenly vanishes. The core collapses. Within seconds or even fractions of a second, matter is compressed to extraordinary density. If the core is massive enough, not even the quantum mechanical pressure between neutrons can halt the collapse. The star becomes a black hole, a region of space-time where the gravitational field is so intense that the escape velocity exceeds the speed of light. Anything that crosses the event horizon of a black hole, matter, radiation, light itself, is gone from the observable universe. It cannot send a signal back. It cannot escape. From the perspective of an outside observer, it seems to simply vanish, swallowed by the void, and black holes grow massive and cold and dark, devouring gas and dust and stars and entire stellar systems, accumulating mass over billions of years, seemingly destroying everything they touch. For a long time, physicists were reasonably comfortable with this picture, even within the framework of quantum mechanics, because the information swallowed by a black hole might be inaccessible to outside observers, but it was still inside the black hole, hidden, not destroyed. The black hole retained a kind of cosmic memory, carrying within its interior the quantum description of everything that had ever fallen in. The total information of the universe was still conserved, just sequestered. Then, in 1974, Stephen Hawking did something remarkable. He applied quantum field theory to the curved space-time geometry around a black hole, and he found something no one expected. Black holes are not black. They glow, not with ordinary light, not with the radiation of the hot gas swirling around them in their accretion disks. That glow is familiar and explicable. Hawking discovered something far stranger, a purely quantum mechanical process by which a black hole very slowly, very faintly emits radiation from the vicinity of its event horizon. This radiation is now called Hawking radiation, and its discovery changed everything about how physicists think about black holes. The mechanism behind Hawking radiation involves the quantum vacuum, one of the strangest features of quantum field theory. Even in what we call empty space, in the total absence of any matter or classical energy, quantum mechanics forbids true emptiness. The Heisenberg uncertainty principle, which governs the relationship between energy and time at the quantum level, means that the vacuum is perpetually churning with activity. Pairs of virtual particles, a particle and its corresponding antiparticle, are constantly flickering into existence and then annihilating each other, borrowing energy from the vacuum for incredibly brief moments allowed by the uncertainty principle. Under normal circumstances, these virtual particle pairs appear and annihilate so quickly that they have no direct effect on the world. They are quantum ghosts, present in the mathematics but invisible in practice. But near the event horizon of a black hole, something different can happen. If a virtual pair appears with one member just outside the event horizon and the other member just inside it, the black hole's gravity can separate the pair before they can annihilate. The particle on the outside escapes into the surrounding space. The particle on the inside falls through the horizon, never to return. The escaped particle is real, carrying real energy, radiating outward from the black hole. But that energy has to come from somewhere. Energy is conserved. The universe demands that the books balance, and so the energy comes from the black hole itself. The black hole loses a tiny, almost inconceivably small amount of mass with each particle that escapes. Over an extraordinarily long time, a time so vast it makes the current age of the universe seem like a brief preliminary, the black hole radiates away its mass entirely. It evaporates. Slowly, and then faster and faster as it grows smaller and hotter, the black hole shrinks and eventually, in a final burst of radiation, it is gone. And here is where the problem begins. Here is where the universe seems to threaten to violate its own deepest laws. Hawking's calculations showed that the radiation emitted by a black hole is thermal. It is random. It contains no information about what fell in. A black hole formed from the collapse of hydrogen gas and a black hole formed from the collapse of an entire library of books would, according to Hawking's calculation, produce exactly the same Hawking radiation, characterized only by the black hole's mass, charge, and angular momentum, the three properties that classical general relativity allows a black hole to retain. These three quantities were already known to be the only distinguishing features of a classical black hole, a principle that physicists somewhat grimly describe as the no-hair theorem, meaning that black holes are featureless compared to the rich complexity of ordinary matter. If Hawking's calculation is correct in its original form, then when a black hole evaporates completely, the information about everything that ever fell into it is simply gone, not hidden somewhere, not encoded in some subtle form in the radiation, just gone. The quantum description of all that matter and energy, the complete specification of every particle's properties, every quantum state, every entanglement relationship between particles, all of it destroyed, annihilated into nothing. And that is the information paradox. It is one of the deepest and most troubling unsolved problems in all of physics. Because on one side you have quantum mechanics, telling you with absolute mathematically ironclad certainty that information cannot be destroyed, that the universe is reversible, that the past is always recoverable in principle from the present. And on the other side you have Hawking radiation, telling you that black holes evaporate and leave nothing behind, that information disappears. Both of these things cannot be simultaneously true. One of our most fundamental theories has to be wrong or incomplete, or we are missing something profound about how the universe actually works. The magnitude of this conflict is difficult to overstate. Hawking himself understood it immediately, and he spent years trying to work out whether it was genuinely a problem or whether there was some way to reconcile the two pictures. For a long time, he believed that information was genuinely lost in black holes, that this was a real and unavoidable breakdown of quantum unitarity, and that the laws of quantum mechanics simply did not apply in the same way near singularities. This was a deeply controversial position, and it drew fierce opposition from other physicists, most notably Leonard Susskind and Gerard 't Hooft, who argued with equal conviction that unitarity had to be preserved, that the laws of quantum mechanics could not simply fail in certain extreme environments, and that the information carried into black holes must somehow be returned to the outside universe in the Hawking radiation. This debate was not merely academic. Susskind himself later described the conflict in his book as a fundamental clash over the nature of physical law, a genuine intellectual war over the foundations of physics. The resolution of the information paradox, if and when it comes, will be one of the most important theoretical discoveries in the history of science. Now, we should acknowledge something here, because this is exactly the kind of frontier territory where the science is still actively developing, where physicists are still debating and arguing and publishing competing frameworks. At Deep Space Intelligence, we try always to be honest about the difference between what we know and what is still being worked out. We encourage you to explore these ideas yourselves, to read the papers, to look up the physicists we mention, to consult sources like the journals Physical Review, Nature Physics, and the preprint archive Arsif where this work is published and debated. The picture we are presenting is our best current understanding, but it is a picture still being assembled. With that said, let us follow the trail of attempts to solve the paradox, because even the attempts are extraordinary, each one opening a door onto a deeper and stranger vision of reality than the one before. The first serious direction came from thinking about entropy. In the early 1970s, a young physicist named Jacob Bekenstein noticed something remarkable about black holes. Entropy, in thermodynamics, is a measure of disorder, of the number of possible microscopic configurations that correspond to a given macroscopic state. The second law of thermodynamics tells us that the entropy of a closed system always increases or stays the same. It never decreases. Now, there was a theorem in classical general relativity proved by Hawking, stating that the surface area of a black hole's event horizon can never decrease. It can grow as more matter falls in, but it can never shrink. Bekenstein recognized the structural parallel between these two statements and argued that it was more than a coincidence. He proposed that black holes genuinely possess entropy, and that this entropy is proportional to the surface area of the event horizon. This was a radical idea. Black holes were supposed to be the ultimate simple objects, characterized by only 3 numbers. How could they have entropy? Entropy is a property of systems with many possible internal states, and classical black holes seem to have essentially no internal states at all. But Bekenstein's intuition was correct. Hawking's subsequent discovery of thermal radiation from black holes confirmed it. Because for an object to emit thermal radiation, it must have a temperature, and objects with temperature have entropy. The Bekenstein-Hawking entropy formula tells us that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck area, the fundamental quantum unit of area derived from the constants of quantum gravity. For a stellar mass black hole, this entropy is almost incomprehensibly large, vastly larger than the entropy of any ordinary piece of matter of the same size. This result is astonishing and deeply informative. It tells us that a black hole's entropy, its information content, its number of possible internal states, is proportional not to its volume but to its surface area. The information about what is inside the black hole seems to be encoded on its two-dimensional boundary, not distributed throughout its three-dimensional interior. This observation, seemingly mundane at first glance, is actually one of the most profound clues in modern physics. It is the seed from which an entirely new vision of reality grew. In the early 1990s, two physicists independently seized on Bekenstein's observation and drew from it a conclusion so radical that it still has the power to stop you cold when you first encounter it. Gerard 't Hooft, a Nobel laureate who had already helped revolutionize particle physics, and Leonard Susskind, working independently and building on ideas from string theory, both argued that Bekenstein's result was not just an interesting fact about black holes, it was a fundamental principle about the nature of space, information, and reality itself. They called it the holographic principle. The holographic principle states that the complete information content of any region of space is not stored throughout the volume of that region, but is encoded on its boundary surface. Just as a two-dimensional hologram can encode all the information needed to reconstruct a three-dimensional image, the two-dimensional boundary of any region of space encodes all the information about everything inside it. The three-dimensional world we experience, the depth and volume of space, the apparent solidity and complexity of matter, may in a deep sense be a kind of projection, an emergent description arising from a more fundamental two-dimensional reality. Susskind put it with characteristic directness. The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. Now, a word of careful clarification is warranted here, because the holographic principle is often sensationalized in popular science. It does not mean that you or I are merely an illusion or a fake. It does not mean that reality is not real. It means something more subtle and in some ways more interesting. The three-dimensional description of reality and the two-dimensional description of reality are different but equivalent languages for describing the same thing. Neither is more or less real than the other. They are dual descriptions of a single underlying physical truth. But for the purposes of the information paradox, the holographic principle carries an immediate and powerful implication. If all the information about everything inside a region of space is encoded on its boundary, then when matter falls into a black hole, its information is encoded on the event horizon. The horizon carries the imprint of everything that has ever crossed it. And when the black hole evaporates through Hawking radiation, that information is not lost. It is gradually, subtly imprinted onto the outgoing radiation through correlations and quantum entanglement that Hawking's original calculation was too crude to capture. The Hawking radiation is not, in this picture, truly random and structureless. It appears random in the same way that the light scattered from a hologram appears to be a random blotch of light and dark until you view it from the right angle and under the right conditions, at which point a three-dimensional image snaps into focus. The information is there. It is just extremely scrambled, encoded in the finest-grained quantum correlations between individual photons emitted across vast stretches of the black hole's lifetime. In principle, an observer equipped with a perfect measuring apparatus and unlimited computational power could take all the Hawking radiation ever emitted by an evaporated black hole and reconstruct from it everything that ever fell in. In practice, of course, this is utterly impossible. The information is more scrambled than anything else in nature. It would take computational resources vastly exceeding anything that could exist in our universe to actually perform the reconstruction. But the principle matters, not the practice. The information is there. It is not destroyed. This holographic resolution of the information paradox gained substantial support from a remarkable theoretical development in 1997 that is known as the ADS/CFT correspondence, or more colloquially as gauge gravity duality. The physicist Juan Maldacena, then at Harvard and now at the Institute for Advanced Study in Princeton, published a paper that has since become the most cited paper in theoretical physics, with more than 20,000 citations to date by some counts, a staggering testament to its impact. What Maldacena showed is this. A theory of quantum gravity in a particular type of spacetime called anti-de Sitter space, which has a characteristic negatively curved geometry, is exactly mathematically equivalent to a quantum field theory without gravity that lives on the lower dimensional boundary of that space. The two theories are dual to each other. Any question you can ask in the gravity theory has an exact corresponding question in the boundary field theory, and vice versa. The boundary quantum field theory is explicitly unitary. It is a standard quantum mechanical system that obeys all the usual rules, including conservation of information. If the two theories are truly equivalent, then the gravity theory, which includes black holes, must also be unitary. Black hole formation and evaporation in anti-de Sitter space must, in principle, preserve information, because the equivalent process in the boundary theory does. Hawking's original calculation was not wrong exactly, it was simply incomplete. It was an approximation that missed the subtle quantum gravitational corrections that would encode the information in the outgoing radiation. Faced with this argument, even Hawking himself eventually conceded. In 2004, at a conference in Dublin, he publicly reversed his earlier position and accepted that information is not destroyed in black holes, that quantum mechanics prevails even in the most extreme gravitational environments. It was a significant moment in the history of physics, one of the most famous capitulations of a profound position by one of the field's most distinguished figures. But accepting that information must be preserved and actually understanding the mechanism by which it is preserved are very different things. The ADS/CFT correspondence told physicists that unitarity must hold, but it did not explain how. What is the actual physical mechanism by which information avoids destruction? How does it get from inside the black hole to the Hawking radiation outside? What actually happens at the event horizon? These questions drove some of the most interesting theoretical work of the following 2 decades, and the answers that physicists are converging on are, to put it mildly, extraordinary. One of the most important clues came from thinking carefully about what happens to information at the event horizon as a black hole ages. A physicist named Don Page, working in the 1970s and 1980s, made a crucial observation about the entropy of Hawking radiation over a black hole's lifetime. Page argued on very general quantum mechanical grounds that if black hole evaporation is unitary, then the entanglement entropy of the radiation emitted by the black hole must follow a specific pattern. Early in the black hole's life, the entropy of the emitted radiation should increase as the radiation accumulates and becomes more entangled with the remaining black hole interior. But at a certain point, roughly when half the black hole's information has been radiated away, the entropy should reach a maximum and then begin to decrease again, returning eventually to zero when the black hole is fully evaporated. This predicted pattern is called the Page curve, and it becomes a kind of benchmark, a prediction that any genuine solution to the information paradox must be able to reproduce. If a proposed mechanism can be shown to produce Hawking radiation that follows the Page curve, entropy rising and then falling symmetrically over the black hole's lifetime, then it has captured something real about how unitarity is preserved. For decades, no one could actually derive the Page curve from first principles in a semi-classical calculation. Hawking's calculation predicted entropy that rose monotonically and never fell, which is the signature of information loss. The Page curve remained a prediction, a target, a statement of what must be true if quantum mechanics holds, but not yet a derivation of how it works. Then, around 2019 and 2020, a series of papers by researchers including Ahmed Almeri, Netta Engelhardt, David Merolf, Henry Maxfield and others achieved something remarkable. Using a set of ideas involving quantum extremal surfaces and what has come to be called the island formula, they were able to derive the Page curve from a semi-classical calculation. They showed, for certain simplified models of black holes, that by including contributions from regions inside the black hole called islands, which are connected to the exterior radiation through quantum gravitational effects, you can reproduce the unitary Page curve. The entropy of the radiation rises, reaches a maximum at the Page time, and then falls back to zero, exactly as unitarity requires. This was a major advance, not a complete solution to the information paradox because the models are idealized and the mechanism involves quantum gravitational effects that are not yet fully understood, but a genuine and exciting step toward understanding how nature actually does it. And underlying all of this is an even deeper and more beautiful idea that has been growing in theoretical physics for the past decade or more. An idea that connects quantum entanglement to the very geometry of space-time in a way that still has the power to leave even seasoned physicists speechless when they sit with it long enough. The idea emerged from a 2013 paper by Juan Maldacena and Leonard Susskind that carries one of the most elegant titles in modern physics. It is called Cool Horizons for Entangled Black Holes, and the central conjecture it contains is written as a deceptively simple equation, ER equals EPR, Let us unpack that. ER refers to the Einstein-Rosen bridge, which is the technical name for a wormhole, a theoretical tunnel connecting two distant regions of space-time. Nathan Rosen was Einstein's collaborator, and in 1935 the two of them described these bridge solutions in the framework of general relativity. EPR refers to the Einstein-Podolsky-Rosen paper, also from 1935, which introduced the concept of quantum entanglement, the bizarre phenomenon by which two particles can share a quantum state such that measuring one instantly determines the state of the other, regardless of the distance between them. For 78 years, these were considered completely separate ideas. Wormholes were a curiosity of general relativity, a mathematical solution that might or might not correspond to anything physically real. Quantum entanglement was a core feature of quantum mechanics, utterly mysterious in its non-local correlations but well verified experimentally. Nobody thought the two had anything to do with each other. Maldacena and Susskind's conjecture says otherwise. It proposes that quantum entanglement between particles and quantum systems is geometrically equivalent to a wormhole connection between them. Two particles that are maximally entangled are connected by an Einstein-Rosen bridge. The non-local correlations of quantum entanglement are not just analogous to space-time connectivity, they are space-time connectivity, expressed in a different language. If the ER equals EPR conjecture is correct, and it has been gaining support from multiple directions in theoretical physics, then it means that the geometric fabric of spacetime itself is knitted together by quantum entanglement. The connectivity of space, the fact that the region around you is smoothly connected to the region 10 meters away, which is connected to the room beyond the wall, which is connected to the street, which is connected to the city, the country, the planet, the solar system, and the galaxies beyond, all of that smooth connected geometry emerges from the pattern of quantum entanglement between the fundamental quantum degrees of freedom of the universe. Mark van Ramsdonk, a physicist at the University of British Columbia, conducted a famous thought experiment that helped set the stage for this idea. He showed that if you take a quantum system that is a union of two entangled parts, and you reduce the entanglement between the two parts, the geometry of the corresponding spacetime splits apart. Reduce the entanglement to zero, and the two regions of spacetime become completely disconnected. The implication is stark. Spacetime is made of entanglement. The geometry we walk through, the space we breathe, the distances between objects that define the structure of the physical world, all of it emerges from quantum correlations between microscopic degrees of freedom. Maldacena, describing the implications of ER equals EPR, said something that I find extraordinarily evocative. He said that without these quantum connections, all of space would atomize. The solid and reliable structure of spacetime is due to the ghostly features of entanglement. Read that again. The solid and reliable structure of spacetime is due to the ghostly features of entanglement. What feels to us like the bedrock of reality, the very framework within which all physical processes occur, the stage on which the entire drama of the universe is played out, is sustained by the quantum connections between things. Cut those connections, dissolve those correlations, and the geometry falls apart. This is the picture that modern theoretical physics is converging on, and it has direct implications for the question we started with, the question of whether anything ever truly disappears. Because if space-time geometry is encoded in quantum entanglement, and if quantum entanglement is conserved by unitary evolution, and if the information contained in any quantum state is indestructible, then the fabric of reality itself is a vast, permanent record of everything that has ever happened within it. When matter falls into a black hole, it does not vanish. It becomes entangled with the quantum degrees of freedom of the event horizon. When the black hole radiates, those entanglements spread into the outgoing radiation. The geometry of the spacetime around the black hole, including the geometric connections described by the ER equals EPR picture, maintains the invisible threads of correlation between the infallen matter and the outside world. Information is not carried away from the black hole by brute force, by some new field or some new particle shooting through the event horizon. It is transmitted gradually, almost imperceptibly, through the quantum entanglement structure of space-time itself. Now, there is something I want to step back and acknowledge here. The ideas we are exploring, from the holographic principle to the island formula to the ER equals EPR conjecture, are some of the most technically complex and mathematically demanding ideas in modern theoretical physics. They have not all been rigorously proven. They apply most cleanly to idealized systems like black holes in anti-de Sitter space, which is not the space-time of the actual universe. The full derivation of how information is preserved in realistic black holes in our universe, in flat or de Sitter space-time rather than the anti-de Sitter geometry of Maldaceno's correspondence, remains an open problem. These are honest limitations, and we say them not to undermine the importance of what has been achieved, but to give you an accurate picture of where the science actually stands. At Deep Space Intelligence, we think it is just as important to know what we do not yet understand as to celebrate what we do. We always encourage you to pursue these questions further, to check the primary literature, to look at the work of the physicists and institutions doing this research, and to form your own carefully reasoned view. The beauty of science is precisely that it does not ask you to simply trust anyone, not even the most eminent researchers. It asks you to follow the evidence and the reasoning, and the evidence and reasoning as they currently stand point strongly toward a universe in which information is conserved, a universe in which nothing truly disappears. But let us pull back from the extremes of black hole physics for a moment, because the implications of conservation, of the indestructibility of information, are not limited to the exotic territories of event horizons and quantum gravity. They permeate everything. They are present in every process, every interaction, every transformation of matter and energy at every scale, from the subatomic to the cosmological. Consider what happens to a human body after death. From a purely physical and biological standpoint, the processes are well understood. The body begins to decompose. Cells that were maintained by metabolic processes during life begin to break down as those processes cease. Bacteria, many of them residents of the digestive system throughout life, begin to consume the tissues. Organic molecules break down into simpler compounds. Water, carbon dioxide, ammonia, hydrogen sulfide, and dozens of other substances are produced and disperse into the surrounding environment. The carbon atoms that were part of bones and muscles and brain tissue become available for uptake by plants, which incorporate them into cellulose and sugars, which are consumed by insects and small animals, which are consumed by larger animals. The cycle continues. Over years and decades, the atoms that once composed a human being are distributed across an enormous volume of soil, water, and air, incorporated into hundreds or thousands of other living organisms, dispersed across the landscape in ways that become exponentially more complex and tangled with time. From the perspective of conservation laws, nothing about this process is mysterious. Every atom is accounted for. Every quantum of energy is tracked, transformed, redistributed, but never destroyed. The second law of thermodynamics tells us that entropy increases, that the ordered, structured information of a living organism disperses into less ordered, more diffuse forms as death and decomposition proceed. But the second law is a statement about macroscopic accessibility of information, not about its fundamental existence. The information is not destroyed. It is scrambled, dispersed, spread across a scale that makes it practically inaccessible and unrecoverable. But in principle, in the language of fundamental physics, it is all still there. There is a concept in quantum mechanics that captures this distinction between practical inaccessibility and fundamental preservation, and it goes by the name of quantum scrambling. When a quantum system undergoes a complex interaction, the information about its initial state gets spread throughout the system in an intricate, highly entangled pattern. The information is not lost, it is scrambled. To retrieve it, you would need to measure the entire system with perfect precision and then perform a computational task of staggering complexity to decode the pattern. In practice, this is impossible for any system more complex than a handful of particles. But the scrambling is reversible in principle. A black hole is the ultimate scrambler. Nothing in nature mixes and entangles information more thoroughly than a black hole's interior. The question of how to reverse the scrambling and recover the original information from Hawking radiation is the informational equivalent of reconstructing a human being from the atoms dispersed across an ecosystem, except harder, by many orders of magnitude. But the fundamental physics is the same. The information is not gone, it is just extraordinarily cosmically scrambled. This brings us to an idea that has become increasingly central in the theoretical physics of black holes over the past decade, an idea connected to a rich body of work on quantum chaos and information scrambling. Physicists have found that black holes are what they call fast scramblers. They thermalize information, mix it into the system as a whole, on a timescale that is remarkably short given the enormous complexity of the system. The characteristic timescale for information to be thoroughly scrambled in a black hole of mass m is proportional to the black hole's mass times the logarithm of the entropy, a timescale called the scrambling time. For a stellar mass black hole, this might be on the order of a fraction of a second. For a supermassive black hole like the one at the center of our galaxy, Sagittarius A star, with a mass of about 4 million times that of the Sun, the scrambling time is still remarkably short compared to astrophysical timescales. But while information is scrambled almost instantly, it is returned incredibly slowly. The Hawking evaporation time for a stellar mass black hole is a number so large that it makes the current age of the universe look like an afterthought. For a black hole of one solar mass, the evaporation time is approximately 10 to the power of 67 years. The current age of the universe is roughly 14 billion years, or about 10 to the power of 10 years. The evaporation time is 10 to the 57th times longer than the current age of the universe. For a supermassive black hole of billions of solar masses, the timescale becomes even more fantastically long. So the information falls in quickly, is scrambled almost instantaneously into the black hole's quantum degrees of freedom, and then leaks back out over timescales that stagger the imagination. It is the ultimate delay line, the universe's most extreme slow-release mechanism for encoded information. Now, in 2016, Stephen Hawking, Malcolm Perry and Andrew Strominger published a paper that offered a new angle on this question, proposing that black holes carry what they called soft hair. Particles that have no rest mass, like photons and gravitons, can exist with arbitrarily low energy. At exactly zero energy, these are called soft particles, and they can exist in infinite numbers without adding any energy to the system. Hawking, Perry and Strominger argued that when something falls into a black hole, it imprints information on the event horizon through these soft photons and gravitons, leaving a kind of residual record on the horizon that is infinitely detailed but carries no energy. Andrew Strominger described it memorably, saying that rather than being a simple, featureless object, a black hole is like a large hard drive which can store essentially an infinite amount of information in the form of these zero-energy particles. The event horizon, in this picture, is not a blank and undifferentiated surface. It is a richly structured record of everything that has ever fallen through it, written in the language of soft particles and asymptotic symmetries of space-time. This picture is not yet complete. The soft hair proposal has generated intense debate, with researchers arguing about whether it truly resolves the information paradox or merely shifts the problem. But it is part of a broader convergence on the view that the event horizon of a black hole is not a passive featureless surface, but an active quantum information-rich boundary carrying the record of its history. And all of this brings us back to the original claim, the one in our title, the one that should genuinely disturb you if you sit with it long enough. According to the deepest laws of physics as we currently understand them, nothing ever truly disappears. Every atom, every quantum of energy, every pattern of information, every event that has ever occurred anywhere in the universe has left its mark, encoded its history into the structure of reality, and cannot be fully erased. The log in the fire does not disappear. The human body does not disappear. The words spoken and forgotten do not disappear. The stars that burned out billions of years before the solar system formed did not disappear. Their light is still travelling outward through the universe, carrying their spectral signatures, their history, their information. Their ash and gas became the nebulae from which new stars formed, from which the solar system condensed, from which the atoms in your body were assembled. You are, in a very literal sense, made of ancient stellar information that has been through multiple cycles of transformation without ever being truly destroyed. Even the oldest and most extreme objects in the universe, the black holes that formed in the first billion years after the Big Bang, are not destroying the matter they consume. They are transforming it, scrambling it, encoding it in the quantum degrees of freedom of their event horizons and the subtle correlations of their emitted radiation. The information is there, hidden in a form we cannot currently read, but present, preserved, indelible. And somewhere in the mathematics of quantum gravity, in the holographic principle, in the island formula, in the ER equals EPR conjecture, in the soft hair on black hole horizons, in all the theoretical scaffolding that physicists have been assembling over the past 50 years, the universe is slowly revealing the mechanism by which it keeps its books. Perfectly. Always. But why should this disturb you? We said at the start that it should, and I have not forgotten that. The unsettling part is not the physics itself. The unsettling part is what it implies about the nature of reality, about the permanence of the past, about what it means for something to end. Because we live our lives with a working assumption of impermanence. Things happen, and then they are over. People live, and then they die, and then they are gone. Fires burn, and then they go cold, and then the warmth is gone. Moments pass, and then they are in the past, inaccessible, irretrievable, finished. But if the physics is right, then none of that is actually true at the most fundamental level. The past is not gone. It is not over. It is encoded permanently in the quantum state of the universe. Every moment that has ever happened is still there, inscribed in the structure of reality, just scrambled beyond any practical hope of reading. The universe keeps a perfect record. It just does not hand it out. This is what I mean when I say it should disturb you. Not because it is frightening exactly, but because it quietly undermines one of the most basic intuitions about reality, the sense that things end, that the past recedes and fades, that the universe moves forward by leaving things behind. The physics says otherwise. The universe does not leave things behind. It carries everything with it, encoded in the finest grain of its quantum state, written in the correlations between particles that will never interact again, preserved in the subtle temperature of radiation that will never be measured precisely enough to be decoded. We are all part of a universe that never forgets. And the deeper you follow this idea, the stranger and richer the implications become. Because conservation of information is not merely a statement about physical bookkeeping. It is a statement about the nature of time, the nature of causality, the nature of identity. If the complete quantum state of the universe at any given moment contains within it the complete history of everything that has ever happened, then the past is not less real than the present. It is equally real. It is all there, implicit in the now, a shadow of every moment that preceded this one still present in the patterns of entanglement and correlation woven through the quantum fields that fill all of space. Some physicists have gone so far as to suggest that this view of quantum mechanics implies a kind of block universe, in which all moments in time are equally real, and the past, present and future all exist simultaneously in a four-dimensional space-time structure. The flow of time, the sense that the past is gone and the future is not yet here, becomes in this view a feature of our subjective experience, our way of navigating the block, rather than a fundamental feature of reality itself. Others resist this interpretation, arguing that quantum mechanics is compatible with a genuinely dynamic universe, where time has an arrow and the present is privileged. The debate between the block universe view and the dynamical view of time is one of the deepest ongoing philosophical disagreements in the foundations of physics, and it is not resolved. But even those who resist the block universe accept the conservation of information. They accept that the quantum state of the universe encodes its complete history, and that nothing is ever truly deleted. The scrambling of information as it disperses into the environment, as a fire burns or a body decomposes or a star collapses, can be understood through a concept called decoherence. When a quantum system interacts with its environment, the delicate quantum superpositions and entanglements that describe its state become spread across an enormous number of environmental degrees of freedom, photons, air molecules, electromagnetic fields, and so on. The system appears to lose its quantum character and behave classically, not because the quantum information is destroyed, but because it becomes hopelessly entangled with the vast complexity of the environment. To recover the original quantum state, you would need to measure the entire environment with perfect precision and reverse compute the original state, a task that becomes impossible for any macroscopic system interacting with the broader world. This process is decoherence, and it is the mechanism by which the quantum world of superpositions and entanglements gives rise to the classical world of definite objects and outcomes that we experience. The quantum information is never destroyed. It is just diluted into the environment until it becomes completely inaccessible in practice. The distinction between the quantum and classical worlds is not a distinction between information-preserving and information-destroying regimes. It is a distinction between information that remains locally accessible and information that has been globally dispersed. And at the cosmological scale, this principle extends to the universe as a whole. The entire history of the universe, from the first quantum fluctuations in the inflationary epoch to the present moment, is encoded in the quantum state of everything that now exists. The light from the first stars, long since decayed and scattered, has left its imprint on the cosmic microwave background and on the atoms it interacted with across 13 billion years of propagation through space. The gravitational waves from the first merging black holes ripple through space-time and carry their history encoded in the subtle stretching and squeezing of space that they produce. The neutrinos from the first supernovae are still streaming through the universe, carrying their information unchanged, passing through matter almost without interacting, racing toward the ends of the observable universe and beyond. The universe is not losing information. It is spreading it out, distributing it more and more widely, making it harder and harder to read for any localized observer, but never, at any level, actually destroying it. The total quantum information content of the universe is, as far as the laws of physics allow us to determine, perfectly conserved, now as it was at the beginning, as it will be long after the last black holes have evaporated and the last photons have dispersed into the cold dark of an expanding universe, approaching its ultimate equilibrium. There is something almost unbearably strange about this vision of reality once you really inhabit it. Imagine standing in a forest and realizing that every sound ever made in that forest is still there, encoded in the quantum states of every molecule in the air, every leaf, every grain of soil, every root and branch and bird. Not accessible, not playable back, not recoverable by any conceivable technology, but there, present, real, preserved by the inexorable mathematics of unitary quantum evolution. Or imagine looking at a patch of empty sky and knowing that the light crossing that region right now carries, in its quantum correlations with other photons emitted across billions of years, a scrambled but theoretically intact record of every source that ever shone in that direction. Ancient galaxies long since merged, stars burned out before the sun existed. Perhaps, in some far-fetched theoretical framework, even the quantum signatures of whatever it is that physics will eventually tell us happened before the Big Bang. The universe keeps its secrets, but it keeps them. It does not discard them. This is the deeper meaning of the phrase we began with. According to physics, nothing ever truly disappears. Not the wood in the fire, not the light from dead stars, not the quantum states of particles that crossed a black hole's event horizon a billion years ago. The universe is one vast, perfectly maintained, infinitely scrambled archive of everything that has ever existed and everything that has ever happened. And somewhere in that archive, encoded in forms we have barely begun to understand, is the complete history of every moment that has ever been. Now, the story does not end here, because while the principle of information conservation is as well established as any in physics, the mechanisms by which it operates in the most extreme environments in the universe are still being worked out, still being debated, still surprising physicists with new implications and new paradoxes that demand new solutions. The frontier of this inquiry leads us into territory that is genuinely strange even by the already strange standards of quantum mechanics and general relativity. There are proposals that space-time itself is made of quantum bits, of elementary units of information at the Planck scale, the smallest meaningful length in physics, about 1.6 times 10 to the minus 35 meters. There are proposals that the event horizons of black holes are actually highly energetic boundaries called firewalls that burn up in falling matter, replacing the smooth and featureless horizon of classical general relativity with a violently quantum surface. There are proposals that black holes are actually giant tangles of quantum entanglement, that their interiors are connected to distant regions of space through wormholes sustained by entanglement between the Hawking radiation and the interior degrees of freedom, resolving the paradox by blurring the very boundary between inside and outside. There is a rich, ongoing, deeply contested theoretical landscape here, and we are going to explore it further. Because once you accept that information is conserved, that nothing truly disappears, you are immediately confronted with new questions that are in some ways even more unsettling than the original one. If all the information is preserved, where exactly is it? How is it encoded? What does it mean for there to be information about something that is behind an event horizon, beyond any possible observation? What is the relationship between information and physical reality in the most fundamental sense? These are not just technical questions for specialists. They are questions about the nature of existence, the nature of the past, the nature of identity and continuity, and what it means for something to be real. And the answers that physics is slowly assembling, piece by piece, framework by framework, paradox by paradox, are answers that could fundamentally reshape how we understand not just the universe out there, but the universe we carry inside us, the universe of thought and memory and meaning, the universe of minds embedded in a physical reality that, it turns out, never truly forgets anything. Let us consider for a moment the deeper strangeness of the vacuum itself, because in some ways the quantum vacuum is the most profound demonstration of the principle that nothing is truly empty, nothing is truly absent, and nothing is truly gone. We tend to think of empty space as a stage, a passive backdrop against which the real action of the universe takes place. But quantum field theory paints a completely different picture. What we call the vacuum, the state of a quantum field with the lowest possible energy, is not empty. It is seething with activity. The Heisenberg uncertainty principle applies not just to particles but to the fields that describe them. Because of the uncertainty relationship between energy and time, the energy of any quantum field cannot be exactly zero, not even in the ground state. There is always a residual, irreducible quantum of energy at every point in space, the zero-point energy, and this energy manifests as constant, rapid fluctuations in the field. Virtual particles, pairs of a particle and its antiparticle, flicker in and out of existence on timescales so brief they cannot be directly observed, but their effects are measurable. One of the most striking demonstrations of vacuum fluctuations is the Casimir effect. If you place two uncharged, perfectly conducting metal plates very close together in a vacuum, a tiny but measurable attractive force appears between them. The explanation involves the quantum vacuum. Between the plates, only certain wavelengths of vacuum fluctuations fit. Outside the plates, all wavelengths are present. The result is an imbalance in the radiation pressure exerted by the vacuum fluctuations on each side of the plates, and this imbalance produces a net force pushing the plates together. The force has been measured experimentally with excellent precision, and it matches the theoretical prediction. Empty space exerts a force. The vacuum is not nothing. This has cosmological consequences of the most dramatic kind. The energy density of the quantum vacuum, summed over all wavelengths and all fields, is related to what cosmologists call the cosmological constant, or dark energy, the mysterious component of the universe that is driving its accelerating expansion. The value of the cosmological constant inferred from observations of the cosmic expansion is one of the most precisely measured quantities in modern cosmology. And yet the naive theoretical prediction of what it should be, based on summing up all the vacuum energies of all quantum fields, gives a number that is roughly 120 orders of magnitude too large. This mismatch, the cosmological constant problem, is widely regarded as the most severe quantitative discrepancy in all of physics. The resolution of this problem, which remains stubbornly unsolved, is likely to require the same kind of revolution in our understanding of space, time, and information that the information paradox has begun to motivate. And the two problems may not be independent. Some of the most promising frameworks for understanding both, including the holographic principle and various approaches to quantum gravity, share deep conceptual roots. The vacuum, then, is not the absence of information, it is the ground state of information. It is the substrate from which particles emerge as excitations and into which they dissolve, while the underlying quantum fields continue their ceaseless fluctuation, encoding and preserving the correlations of every interaction that has ever occurred within them. Even nothing in the quantum world is not actually nothing, and this circles back to the central and quietly disturbing truth of this whole inquiry. We began by asking whether anything truly disappears, and the answer that physics delivers, from the conservation of energy to the conservation of quantum information, from the thermodynamics of black holes to the holographic principle, from the structure of vacuum fluctuations to the ER equals EPR conjecture, is consistently and emphatically no. Nothing disappears. The universe is not losing things. It is transforming them, entangling them, distributing their information across larger and larger scales, weaving the past into the fabric of the present in forms that are increasingly scrambled and inaccessible, but never ever erased. The campfire analogy we began with now seems almost quaint against the backdrop of what we have explored. The wood and the fire and the warmth and the smoke are a small illustration of a principle that runs from the smallest virtual particle flickering in the quantum vacuum to the largest black hole in the observable universe and beyond. At every scale, in every process, the universe keeps its accounts. The information is conserved. The record is complete. Nothing is truly lost. This principle, this deep and somewhat vertiginous truth, raises questions that we have only begun to approach in this first part of our exploration. Because if information is truly conserved, if the complete quantum record of everything is preserved in the state of the universe, then what does that imply about the nature of time, about whether the past is as real as the present, about whether identity persists in any meaningful sense when the physical substrate of a person or an object disperses into the environment? These are the questions that will take us deeper still, into the territory where physics begins to shade into philosophy and cosmology begins to raise questions that cut right to the heart of what it means to exist. The question of what it means to exist, to persist, to be real across time, is one that the physics of information conservation does not answer but refuses to leave alone. It keeps pushing at the edges of it, revealing new layers of strangeness with each advance. And the deeper you pull at this thread, the more you find that it is tangled with every other deep question in physics, from the nature of quantum measurement to the origin of the arrow of time, to the question of whether the laws of nature themselves carry some kind of cosmic memory. These are not peripheral puzzles. They sit at the absolute center of what physics is trying to understand about reality, and the information conservation principle illuminates all of them with a strange and unsteady light that reveals as much shadow as it does structure. And the deeper you go, the more you find that the boundary between physics and philosophy, between what science can demonstrate and what it implies, becomes thinner and harder to locate with confidence. One of the deepest implications of the conservation of information is what it suggests about the nature of time itself. We experience time as a flow, a directed movement from past to present to future, with the past receding irretrievably behind us and the future not yet existent ahead. The present moment feels privileged, uniquely real in a way that past and future do not. This is such a fundamental feature of conscious experience that it seems almost self-evident. Of course, the past is gone. Of course, the future has not happened yet. Of course, only now is real. But the laws of physics, as they currently stand, do not actually support this intuition. And the theory that most dramatically undermines it is the one we encounter the moment we accept conservation of information seriously. Einstein's special theory of relativity, formulated in 1905 and confirmed to extraordinary precision by more than a century of experiment, tells us that there is no absolute present shared by all observers. Two observers moving relative to each other will disagree about which events are simultaneous, and neither is wrong. Simultaneity is relative. The present is not a universal feature of reality, but a perspective-dependent slice through the four-dimensional structure of space-time. This is the starting point of what physicists and philosophers call the block universe, or eternalism. If there is no absolute present, if different observers slice space-time into past, present, and future in different ways, then the most natural description of reality is one in which all moments in time are equally real, existing together in a four-dimensional block of space-time. The past is not gone. It is simply elsewhere in space-time, spatially accessible to a different kind of observer, a hypothetical being who could navigate the temporal dimension the way we navigate space. The future has not failed to arrive. It is already there, waiting at a different temporal coordinate in the block. Under this view, which has been argued for by philosophers and physicists from the 1960s onward, and which finds support in both special relativity and in the mathematical structure of quantum mechanics, nothing is ever truly absent. The campfire, burning in a different time, is not gone. The people who lived centuries before us are not gone. The stars that will form billions of years from now are not absent. They are all there, in the four-dimensional structure of space-time, at different coordinates than the one we currently occupy, but equally real. The philosopher and physicist Julian Barber has developed an extreme version of this view, arguing that time itself is an illusion, and that what exists is a timeless configuration space he calls Platonia, in which every possible configuration of the universe exists simultaneously, and what we experience as temporal flow is simply a feature of how our memories connect certain of these configurations. The experience of time passing is real in his view, but the passage itself is not. The past is not gone because it never moved. It always exists, frozen in the mathematical landscape of all possible configurations. This is speculative and controversial, and many physicists and philosophers resist it strongly. But it emerges naturally from taking seriously the mathematical structure of general relativity, in which time is just another dimension of space-time on a certain mathematical footing with the three dimensions of space. And it fits naturally with the conservation of information, which tells us that the quantum state of the universe at any moment contains within it the complete record of every moment that has come before. Now, whether or not one accepts the block universe interpretation, the practical implication of information conservation remains the same. The past is encoded in the present. Not metaphorically, not approximately, but literally and precisely, in the quantum correlations between the particles that make up the present state of the universe. Every quantum state carries the fingerprint of the history that produced it. The universe is a vast palimpsest, a manuscript written and rewritten over billions of years, each new layer of writing inscribed over the last without erasing it, all of it still there if you could read it. And here is where the concept of quantum scrambling, which we introduced earlier, becomes philosophically significant rather than merely technically interesting. Scrambling is the process by which information becomes hopelessly entangled with an enormously complex environment, spread so widely and so thoroughly that no practical observer can ever reconstruct the original state. It is the quantum analogue of stirring a drop of ink into the ocean. The ink does not disappear. Its molecules are still there. Every single one is accounted for. But any realistic experiment you could ever perform would fail to detect the original drop. Its information has been dispersed beyond practical recovery. A burning book undergoes exactly this kind of scrambling. The information encoded in the arrangement of ink on the pages, the words, the sentences, the ideas, does not cease to exist when the book burns. It is transformed, dispersed, redistributed. The carbon atoms that were ink become carbon dioxide. The specific arrangements of those atoms that encoded letters and words and meanings are scrambled into the thermal motion of gas molecules and the infrared radiation emitted by the fire. The information is in there, somewhere, scrambled into the collective quantum state of every molecule that interacted with the fire. But for any conceivable practical purpose, it is unrecoverable. It is, for all meaningful purposes, gone. But only for all meaningful purposes, not actually, fundamentally, physically gone. This distinction matters so much that it is worth dwelling on it a little longer, because it is easy to hear the statement that information is never destroyed and immediately dismiss it as a technicality, as a kind of physicist's pedantry that has no bearing on the real world. After all, if the information can never be recovered, does it matter whether it still exists in some abstract theoretical sense? The pragmatist in us wants to say no. If there is no possible experiment that can ever read the information, then in what meaningful sense is it there? But this would be a mistake, and not just a philosophical one. The conservation of information in the formal sense of quantum unitarity is not a minor footnote or an untested abstraction. It is a consequence of the same mathematical framework that gives us the transistor, the laser, the magnetic resonance imaging machine, and every other technology built on quantum mechanics. The unitarity of quantum evolution is part of the same package as the quantization of energy levels, the Pauli exclusion principle, and the entanglement correlations that now underpin quantum cryptography and quantum computing. If unitarity were violated, if information were genuinely destroyed in physical processes, it would not just affect black holes and philosophy. It would unravel the mathematical consistency of quantum mechanics as a whole, and with it, everything built upon quantum mechanics. The stakes of this principle are not abstract. They are as concrete as anything in science. The reason the scrambled information feels so irretrievably gone, and genuinely is for all practical purposes, lies in the exponential complexity of the scrambling process. When a quantum system interacts with an environment, the number of degrees of freedom involved grows explosively. A single quantum bit interacting with a gas of 1 billion molecules would need to entangle with all of them. To reverse the process and recover the original quantum bit, you would need to measure all billion molecules simultaneously with perfect precision, and then solve an inverse problem of extraordinary mathematical difficulty. The computational resources required scale exponentially with the number of interacting particles, so quickly that even for quite modest systems, the required resources exceed anything that could exist in the physical universe. The scrambling is not practically reversible in any realistic sense. But the information is still there, in the entanglement structure of the billion-molecule quantum state. This tension between practical irreversibility and fundamental reversibility is one of the deepest puzzles in physics. It is the puzzle of the arrow of time, the question of why the second law of thermodynamics, which says that entropy always increases, seems to define a direction for time in a universe whose fundamental laws are time-symmetric. The laws of physics look the same when you run time backward. An electron scattering off a proton and reversing its trajectory obeys exactly the same laws as the original collision. A system of particles interacting under electromagnetic and gravitational forces can be reversed in time, and the reversed motion is equally valid, equally consistent with the fundamental equations. Now, there is a subtlety here worth acknowledging. At the level of the weak nuclear force, the laws of physics are not exactly time-symmetric. The standard model of particle physics includes a combined symmetry called CPT, where C stands for charge conjugation, P for parity or mirror reflection, and T for time reversal. This CPT theorem, one of the most rigorously proven results in quantum field theory, states that the combined transformation of replacing every particle with its antiparticle, reflecting all spatial coordinates, and reversing time leaves all physical laws invariant. But individually, each of these transformations can be violated. The weak nuclear force violates the combination of charge conjugation and parity, called CP symmetry, and through the CPT theorem this implies a small but real violation of time reversal symmetry as well. This was first directly observed in 1998 by experiments at CERN and Fermilab. However, this microscopic T violation at the level of the weak force is far too small and too specific to account for the overwhelming thermodynamic arrow of time we experience in everyday life. The direction of time for macroscopic processes, the reason heat flows one way, the reason entropy increases, the reason clocks run forward and not backward, is not due to this tiny fundamental T violation. It is due to initial conditions, to the fact that the universe started in an extraordinarily low entropy state and has been evolving toward higher entropy ever since, and yet the world we see is profoundly time-asymmetric. Eggs break but do not unbreak. Heat flows from hot to cold but not the reverse. Coffee mixes with cream but the mixed coffee does not spontaneously unmix. Stars burn out but burned-out stars do not spontaneously reignite. We never see a wave spontaneously gathering from across an ocean and focusing on a rock, even though such a motion would be a perfectly valid time-reversed version of an outgoing wave. The arrow of time is everywhere in our experience, and yet, at the level of fundamental microscopic dynamics and setting aside the weak force, nowhere in our fundamental equations. The resolution of this paradox, as Ludwig Boltzmann understood in the 19th century, and as physicists have been elaborating ever since, lies in statistics and initial conditions. The reason entropy increases is not because the fundamental laws of physics forbid it from decreasing, but because states of high entropy, states of great disorder and complexity, vastly outnumber states of low entropy, states of order and structure. Starting from any typical state, the overwhelmingly probable future trajectory leads to higher entropy. Running a typical high entropy state backward would require an extraordinarily finely tuned initial condition, so precisely specified that the probability of it occurring naturally is essentially zero on any timescale we could contemplate. But the universe did begin in such a state. The observable universe at the time of the Big Bang was in an extraordinarily low entropy configuration, smooth and nearly uniform, with only tiny quantum fluctuations to seed the structure that later grew into galaxies and stars and planets. Roger Penrose, the British mathematical physicist who shared the Nobel Prize in Physics in 2020 for his work on black holes and singularities, has been particularly emphatic about this. In his view, the extraordinarily low entropy of the universe's initial state is the deepest fact in cosmology, requiring an explanation that goes beyond standard Big Bang theory. Penrose has spent decades arguing that the smooth initial state of the Big Bang reflects a profound constraint on the geometry of spacetime, specifically on a quantity called the Weyl curvature, which measures certain aspects of the gravitational field's tidal distortion. His Weyl curvature hypothesis proposes that at any initial cosmological singularity, the Weyl curvature must be zero or very small, while at final singularities like those inside black holes it can be arbitrarily large. This asymmetry between initial and final states provides the ultimate source of the thermodynamic arrow of time, the reason entropy increases in the future direction and not in the past direction. Taking this idea further, Penrose developed a speculative but mathematically sophisticated cosmological model called conformal cyclic cosmology, or CCC. In this framework, the universe undergoes an infinite succession of eons, each beginning with a Big Bang and ending in a distant future where all massive particles have decayed or been absorbed into black holes, leaving only massless particles, photons and gravitons, which have no intrinsic experience of time. In this state of massless, radiation-dominated equilibrium, the universe looks geometrically identical after a conformal rescaling to the smooth, featureless geometry of a new Big Bang. The end of one aeon becomes the beginning of the next. The information from the previous aeon is not exactly lost in this picture. It can leave traces in the new aeon, carried across the conformal boundary by gravitational waves and other effects. Penrose and his collaborators have searched the cosmic microwave background for signatures of these traces, looking for anomalous circular patterns that might be the ghostly imprint of particularly massive black holes from a previous cosmic era. The results have been disputed, with some researchers claiming to find tentative evidence, and others arguing the patterns are statistical artifacts. The science here is genuinely unsettled, but the deep ambition of CCC is to find a picture of the universe in which nothing is ultimately lost, in which the information of each aeon is recycled into the next in a kind of cosmic reincarnation of structure and memory. Whether the model is correct or not, the impulse behind it reflects the same deep conviction that underlies the whole story we have been telling. The universe does not waste, it transforms. Now let us return to the frontiers of the black hole information paradox, because in the years since we left off, the story has become considerably more dramatic. The island's formula and the recovery of the Page curve, which we described in Part 1, represent genuine theoretical progress. But they have also sharpened an old and particularly disturbing version of the paradox called the firewall problem. In 2012, 4 physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that sent shockwaves through the theoretical physics community. Their argument, known by the acronym AMPS for the authors' names, began with 3 seemingly uncontroversial assumptions. First, that Hawking radiation is in a pure quantum state, meaning that information is preserved in the radiation. Second, that the information in the radiation comes from the region near the horizon, with standard quantum field theory applying beyond a small distance from the horizon. Third, that an observer falling into a black hole encounters nothing unusual at the event horizon, experiencing only smooth, normal spacetime as they cross it. These 3 assumptions had all seemed reasonable and individually well motivated. The first follows from unitarity, the second from the holographic principle, the third from the equivalence principle of general relativity, which says that an infalling observer should not be able to distinguish free fall near a black hole from free fall in empty space. But AMPS showed that these 3 assumptions cannot all simultaneously be true. If Hawking radiation is to be in a pure state, the outgoing radiation must be maximally entangled with the earlier radiation already emitted so that the total system remains pure. But quantum mechanics has a monogamy of entanglement principle. A particle cannot be maximally entangled with 2 different systems simultaneously. If the outgoing Hawking particle is maximally entangled with the earlier radiation to ensure purity, it cannot also be entangled with its partner falling into the black hole interior. But the smooth, undisturbed horizon of the equivalence principle requires precisely this interior entanglement to exist. The resolution proposed by AMPS was dramatic and unsettling. They argued that when a black hole has radiated more than half its initial entropy, the smooth event horizon must be replaced by a firewall, a wall of extremely high-energy quantum field excitations at the horizon itself. An observer falling into a black hole would not glide smoothly through an uneventful horizon. They would be incinerated. The equivalence principle would be violated in the most violent possible way. This was, and remains, a deeply uncomfortable conclusion. The equivalence principle is one of the foundational pillars of general relativity, verified to extraordinary precision by every experiment ever conducted. The idea that it could simply be violated at the horizon of any sufficiently old black hole is extraordinarily radical. And yet the logic of the AMPS argument is hard to dispute if you accept its 3 starting assumptions. The response from the community was fierce and creative. Leonard Susskind offered a slightly different interpretation, in which the horizon retains smooth properties, but the singularity effectively migrates outward toward the horizon over time, producing firewall-like behavior at the point of merger. Others argued that various assumptions underlying the AMPS argument are subtly flawed. The ER equals EPR conjecture of Maldacena and Susskind, proposed in 2013 partly in response to the firewall paradox, offered a way out by suggesting that the entanglement between the outgoing Hawking radiation and the black hole interior is not violated but is instead geometrically expressed as a wormhole, resolving the apparent contradiction by changing the geometry of the space rather than severing the entanglement. And the island formula results of 2019 and 2020 also speak to this puzzle, suggesting that the interior of the black hole, the island, contributes to the entropy calculation of the radiation in a way that restores unitarity without requiring firewalls. The mechanism is subtle and involves quantum gravitational effects that we do not yet fully understand, but it points toward a resolution that preserves both the purity of the radiation and the smooth crossing of the horizon, at least in the simplified models where the calculations have been performed. The firewall debate illustrates something important about where physics stands right now. We have multiple theoretical frameworks that each capture part of the truth, that each make progress on the information paradox from a different angle, and that are not yet fully reconciled with each other. The holographic principle, ADS/CFT, soft hair, ER equals EPR, and the island formula all point toward the same conclusion, that information is preserved, that black hole evaporation is unitary, but they do not yet form a single unified picture. The complete theory of quantum gravity that would reconcile them all remains to be found, and it is worth pausing here to acknowledge just how extraordinary this situation is. We are talking about theoretical frameworks so mathematically sophisticated that even summarizing them requires careful attention to get right. The physicists working on these problems are operating at the absolute cutting edge of human knowledge, in territory where the mathematical tools barely exist yet, where new machinery has to be invented alongside new physical insights, where the questions themselves are so deep that even knowing what to ask requires years of training and immersion in the field. At Deep Space Intelligence, we believe that one of the most important things we can do is give you an honest sense of this frontier, not just the exciting headline conclusions, but the genuine uncertainty, the active debates, the things we do not yet know. We always encourage you to read beyond what we present here, to look at the work of the physicists and institutes at the frontier of this research, to form your own understanding through engagement with the actual science. That is how knowledge advances, not through accepting any single account, but through the collective, critical, iterative work of many minds engaging with the evidence. With that said, let us zoom out from the extremes of black hole physics and look at the information conservation principle from a different angle, one that touches on the grandest possible scales, the long-term fate of the universe. Our current best cosmological model tells us that the universe is expanding and that this expansion is accelerating, driven by the mysterious dark energy that comprises roughly 68% of the total energy content of the universe. If this acceleration continues, the distant galaxies we can currently see will eventually recede beyond our cosmic horizon, moving away from us faster than light can bridge the gap. They will become forever inaccessible, vanishing from our observable universe not into nothing but into the unreachable beyond, their light increasingly redshifted until it can never reach us. The observable universe will effectively shrink as distant regions pass beyond the cosmological horizon. Stars will continue to form from the remaining gas for perhaps 1 to 100 trillion years, before the raw material for star formation is exhausted. After that, the universe will gradually grow darker and colder as existing stars run out of fuel and die. The last ordinary stellar objects, the faint red dwarf stars that burn their hydrogen so slowly that some might shine for 10 trillion years, will eventually exhaust their fuel and become dark, cooling stellar remnants. White dwarfs, neutron stars, and black holes will dominate the landscape. Over extremely long timescales, even protons may decay, if certain theories of grand unification are correct, and ordinary matter as we know it will dissolve into leptons and photons. Current theoretical estimates put the proton lifetime at more than 10 to the 34th power years, so this is not an imminent concern, but it places an ultimate limit on the lifetime of matter as we know it. By the time ordinary matter has disappeared, the universe will be populated almost entirely by black holes, and then, over timescales that make the current age of the universe look like a brief preliminary, those black holes too will evaporate through Hawking radiation, their mass slowly converted into a dim bath of photons and other particles dispersing into the expanding void. The last black holes, the most massive ones, will evaporate after approximately 10 to the 100 power years. After that, the universe enters what cosmologists call the dark era, populated only by a sparse and ever-thinning gas of low-energy photons, electrons, positrons and neutrinos, drifting through an endlessly expanding space-time approaching, but never quite reaching, a state of perfect thermal equilibrium. This is the heat death, the ultimate thermodynamic fate of the universe, in which all available energy has been degraded to its lowest possible form, in which no further thermodynamic processes can occur, in which the stars have gone cold and dark and the black holes have dissolved, and the particles have dispersed so thoroughly that no future event of any significance can ever take place. It is by any measure the most desolate imaginable vision of the far future. But here is what makes it so philosophically strange in the light of information conservation. Even in the heat death, even in the absolute maximum entropy state of the universe, the information is not gone. It is simply maximally scrambled. The quantum state of the universe in the heat death still encodes, in principle, the complete history of everything that ever happened. Every star that ever burned, every living creature that ever existed, every thought that was ever thought, every book that was ever written, every galaxy that ever formed and merged and scattered its stars, all of it is still there, preserved in the quantum correlations between the sparse cold photons drifting through the void, unreadable, unrecoverable by any process that the physics of that era could support, but there, inexhaustibly, in principle, forever. The archive of the universe does not close, it simply becomes impossible to access. And here the Poincaré recurrence theorem introduces one of the most mind-bending ideas in all of classical mechanics, an idea that becomes even stranger when extended to quantum systems. The French mathematician Henri Poincaré proved in 1890 that any bounded dynamical system will, given sufficient time, return to a state arbitrarily close to its initial state. The system wanders through its accessible phase space, and, because the phase space is bounded and the dynamics are volume-preserving, it must eventually come back near to where it started. For most macroscopic systems, this recurrence time is so fantastically large that it makes the heat-death timeline look like an instant. For a system as complex as even a glass of water, the Poincaré recurrence time exceeds anything we could meaningfully write down, but it is finite. For the universe as a whole, in a quantum mechanical framework, analogous recurrence theorems suggest that the quantum state of the universe will eventually fluctuate back to a configuration closely resembling any previous state, including the extraordinarily low entropy structured state of the early universe. The timescale for this quantum recurrence is something like 10 to the power of 10 to the power of 10 to the power of the entropy of the universe, a number so incomprehensibly large that it bears no relationship to any timescale we ordinarily contemplate, but it is finite. And in that distant, almost inconceivably far future, the information encoded in the universe's quantum state could, in principle, remanifest as structure. This is not a prediction. It is not a consequence of any physical theory we currently have good reason to believe, and the assumptions required for such a recurrence are so stringent, particularly regarding the fate of quantum information in an eternally expanding universe, that many physicists doubt it applies to our actual cosmos. But it is a mathematical consequence of taking seriously the conservation of quantum information in a bounded system. The universe, if it is such a system and if nothing more fundamental prevents the recurrence, would eventually, over timescales beyond any normal reckoning, cycle back through its own history. The information is never lost, it simply waits. There is another theoretical framework we have not yet explored that deserves mention here, and it is one that approaches the question of what happens at the extreme end of gravitational collapse from a completely different angle than string theory or holography. This is loop quantum gravity, developed principally by Carlo Rovelli at the Centre de Physique Théorique at Aix-Marseille University and Lee Smolin at the Perimeter Institute in Canada, building on foundational mathematical work by Abhay Ashtekar at Pennsylvania State University in 1986. In loop quantum gravity, spacetime itself is quantized at the Planck scale, the smallest meaningful length in physics at approximately 1.6 times 10 to the minus 35 meters. Rather than a smooth continuous manifold, Space in this framework is a network of discrete quantum units called spin networks, graphs whose edges carry quantum labels related to the area of the surfaces they cross, and whose nodes carry information about the quantum volumes they bound. Space, in this picture, is granular at its most fundamental level, like a fabric whose apparent smoothness, when viewed up close enough, resolves into individual threads. In 1994, Ravelli and Smolin proved that the quantum operators for area and volume in this framework have a discrete spectrum. Geometry is quantized. The minimum possible area is roughly 10 to the minus 70 square meters, far below anything we could ever directly probe experimentally, but fundamental to the theory. And this quantized geometry carries with it a natural information bound. There is only so much information that can be stored in any finite volume of space, because there are only finitely many quantum degrees of freedom in any finite region. The holographic bound on information, which we derived earlier from black hole thermodynamics, emerges here from the quantization of geometry itself. Two completely different theoretical frameworks arriving at the same conclusion is one of the strongest kinds of theoretical evidence in physics. In 2014, Ravelli and Francesca Vidotto proposed that inside every black hole, at the point where classical general relativity predicts a singularity, a point of infinite density where the laws of physics break down, quantum gravitational effects would instead create what they call a Planck star. When the infalling matter reaches the Planck density, the enormous quantum pressure that loop quantum gravity predicts would halt the collapse and eventually reverse it. The interior of the black hole would not be a singularity at all, but a compressed, intensely hot quantum object, bouncing outward on a timescale that, from the perspective of the collapsing material, might be relatively brief, but which, due to the extreme gravitational time dilation near the Planck scale, would appear from the outside as an almost unimaginably long wait before the bouncing matter re-emerges. In this picture, black holes do not destroy information. They compress it to Planck densities, hold it, and eventually return it. This is, again, a hypothesis, and one that faces serious theoretical challenges, but it illustrates something important about the current state of the field. There are multiple competing frameworks, each internally consistent, each making contact with certain aspects of the problem, none yet definitively established as the correct description of what actually happens at the quantum gravity scale. The honest position is to acknowledge this uncertainty, while recognizing that all the serious candidates point in the same direction on the question of information conservation. None of them requires information to be fundamentally destroyed. Every approach worth taking seriously preserves the quantum state one way or another. Now all of this leads us to a deeper question that the physics keeps circling but cannot fully answer from within its own framework. What is information? Not in the technical sense of Claude Shannon's mathematical theory of communication, the bit-counting, entropy-measuring framework that underlies all of modern information technology, which Shannon developed at Bell Labs in 1948, and which transformed everything from telecommunications to computing to cryptography. Shannon's information theory is extraordinarily useful and deeply profound in its own right, quantifying information in terms of probability and surprise and channel capacity in ways that have shaped the entire information age. But it treats information as something systems carry, a property that can be measured and transmitted and stored, not as something that might be the fundamental substrate of physical reality itself. The physical question is different. When physicists say that the quantum state of a system encodes information about its history, what exactly is being said? Is information a feature of physical systems, a secondary property they happen to have alongside their mass and charge and spin? Or is information something more primary, more fundamental, the substance from which mass and charge and spin and all the rest of physical reality are ultimately constructed? One answer, increasingly popular among physicists, is that information is fundamental. Not secondary to matter and energy, not a property that matter and energy happen to have, but something at least as fundamental as matter and energy, perhaps more so. John Archibald Wheeler, the American physicist who worked with both Einstein and Bohr, who coined the terms black hole and quantum foam in it from bit, who supervised the doctoral dissertations of Richard Feynman and Hugh Everett, and many others who went on to revolutionize physics, spent the later decades of his life promoting a slogan that he considered to express the deepest feature of reality. He called it from bit. The idea is that every particle, every field, every aspect of space-time geometry derives its existence, its activity, its meaning, from binary choices, from yes or no answers to yes or no questions, from bits of information. The physical world is, at its most fundamental level, built from information. Wheeler's own summary of this idea was characteristically pithy. Every every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely from binary choices, from bits. What we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, all things physical are information theoretic in origin, and this is a participatory universe. This is not a mainstream position, and Wheeler himself did not claim it was proven. But it captures something that many physicists feel, intuitively, after engaging with the holographic principle and the ADS/CFT correspondence and all the other results we have discussed. The fact that the information content of a region of space is bounded by its boundary area rather than its volume, that the three-dimensional physical world can be completely described by a two-dimensional surface encoding, that wormholes and quantum entanglement are the same thing expressed in different languages. All of these results suggest that the relationship between information and physical reality is far deeper than we ordinarily recognize. If information is fundamental, then the conservation of information is not just a consequence of other laws, but is itself the deepest law, the one that all the others ultimately rest upon. The laws of physics, in this view, are not laws governing the behavior of matter and energy, with information conservation as a secondary consequence. They are laws governing the behavior of information, with matter and energy as emergent patterns in the information landscape. This idea resonates with another very active area of research that we have not yet fully explored, the connection between quantum information theory and the geometry of space-time. We touched on Mark van Ramsdonk's thought experiment earlier, which showed that the geometry of space-time is sustained by quantum entanglement. But it is worth dwelling on this point more carefully, because the result is more specific and more remarkable than a general correlation. Van Ramsdonk, a physicist at the University of British Columbia, published a paper in 2010 titled "Building Up Space-Time with Quantum Entanglement." He considered a quantum system that consists of two entangled parts, each describing a patch of space-time. Using the ADS/CFT correspondence, he could calculate how the geometry of the corresponding space-time depends on the amount of entanglement between the two parts. His result was stark. Maximum entanglement corresponded to a single, smoothly connected space-time. As the entanglement was reduced, the connection between the two space-time regions weakened. At zero entanglement, the connection disappeared entirely, and the two regions became completely separate, disconnected spacetimes. The geometry of spacetime is not a fixed backdrop. It emerges dynamically from the pattern of quantum entanglement in the underlying quantum system. This is a startling conclusion. What we experience as the smooth, continuous fabric of space, the arena in which all physical events take place, is not primary. It is emergent. It is a consequence of the entanglement structure of a quantum system that lives, in a holographic sense, on a lower dimensional boundary. The solid world we inhabit is the shadow of a quantum pattern. Other researchers have shown that the equations governing the curvature of spacetime in general relativity can in certain contexts be derived from the equations governing the flow of quantum information. The physicist Erik Verlinde of the University of Amsterdam has developed the idea of entropic gravity, proposing that gravity itself is not a fundamental force, but an entropic force, a macroscopic consequence of the tendency of quantum information to spread and disperse. In his framework, gravity arises from the same statistical tendency that causes a polymer to contract when heated, or a gas to expand into available volume. It is not a force in the traditional sense, but a statistical consequence of information thermodynamics at the holographic boundary. This idea is controversial and not universally accepted, but it is taken seriously by many researchers, and it has inspired a substantial body of follow-up work. And it connects naturally with the Jacobson derivation, published by physicist Ted Jacobson at the University of Maryland in 1995, which showed that Einstein's field equations, the equations at the heart of general relativity, describing how spacetime curves in response to energy and matter, can be derived from the thermodynamics of local Rindler horizons, together with the Bekenstein-Hawking entropy formula. In other words, the fundamental equation of gravity can be written as a thermodynamic equation, a statement about the entropy and temperature of quantum information at a certain class of surface. If gravity is a consequence of quantum information dynamics, then the deep structure of the physical world, the curvature of space-time, the attraction between masses, the formation of black holes, and the expansion of the universe, all of it is ultimately a story about information. The universe is not a collection of things that also have information. The universe is information, expressing itself in the language of matter and energy and space-time, and in that universe nothing ever truly disappears, because nothing is anything other than a pattern in the information. Patterns can transform and spread and scramble and disperse, but they cannot cease to exist. The conservation of information is not a law that information must obey. It is a consequence of what information is. You cannot destroy a pattern in the fundamental information of the universe for the same reason you cannot destroy a number. The number 5 does not cease to exist when you stop thinking about it. It is a feature of the mathematical structure of reality, and mathematical structures are not the kind of things that can be destroyed. Now, a word of honest epistemic humility is important here, and we say it because we mean it. The idea that the universe is fundamentally information, that information is more basic than matter, that gravity and space-time emerge from information dynamics, is a speculative framework, not an established fact. It is a perspective shared by many serious theoretical physicists, motivated by strong mathematical evidence, but it is not proven and it is actively debated. The evidence from ADS/CFT is compelling, but applies to specific simplified universes, not necessarily to our own. The holographic principle has strong theoretical support but has not been directly tested experimentally in the way that, say, the predictions of general relativity have been. The ER equals EPR conjecture is beautiful and powerful but is still a conjecture, and there are researchers who question aspects of its foundations. We present these ideas not as settled science, but as the frontier of scientific thought, the direction in which the evidence and the mathematics are pointing. We always encourage our audience to approach these ideas with the same critical curiosity that the physicists themselves bring to them, neither dismissing them as mere speculation nor accepting them uncritically as established truth. This is deep water, and navigating it requires care. The scientific process itself is the best tool we have, and it is worth trusting. At the same time, it is worth distinguishing clearly between the speculative cutting edge and the well-established core. The conservation of energy is not speculative. It is one of the most precisely tested principles in science, confirmed by every experiment ever performed with measuring instruments sensitive enough to check it. The unitary evolution of quantum states is not speculative. It is the mathematical foundation on which quantum mechanics is built, and quantum mechanics has been tested to extraordinary precision across every regime we can probe. The thermodynamics of black holes, the Bekenstein entropy formula, and Hawking's prediction of thermal radiation from black holes represent solid theoretical results derived from well-established frameworks, even if the details of how unitarity is maintained during black hole evaporation remain an open question. The holographic principle has strong evidence from multiple theoretical directions. The overall picture, that information is conserved and nothing is truly destroyed, rests on ground that is much firmer than the speculative extensions at the frontier. With that caveat in place, let us sit for a moment with the full weight of what all of this means. Because even in the most conservative, most cautious reading of the evidence stripped of all speculative extension, the conclusion remains genuinely startling. There is something else worth contemplating as we approach the end of this journey. We have been talking mostly about extreme environments, burning logs, collapsing stars, evaporating black holes, the deep future of the cosmos. But the conservation of information applies with equal force to the mundane world of everyday experience. Right now, in this moment, you're embedded in a vast web of quantum entanglements, connecting every particle in your body to every other particle that has ever interacted with them. Your atoms have been part of countless other structures before they were part of you. They have been part of the ocean and the soil and the atmosphere and other living things. Each interaction they have had has left quantum correlations, traces of their history entangled into the broader quantum state of the world. The air you're breathing right now contains molecules that have passed through the lungs of every person who has ever lived. The carbon dioxide that Julius Caesar exhaled on his last breath has been recycled through the biosphere for more than 2,000 years, and some fraction of it is statistically almost certain to be in the room with you. This is a well-known calculation in atmospheric chemistry. But at the quantum level, the entanglement goes deeper than chemistry. Every photon of sunlight that has ever struck your skin and scattered off its surface has carried some record of that interaction into the environment, spreading correlations outward at the speed of light. The electromagnetic fields you have perturbed simply by existing, by moving through space, by speaking, by generating heat, have all left their marks on the quantum state of the world around you. You have been writing the universe's archive since the moment the atoms that constitute you were first assembled, and the universe has been faithfully recording every word. This is not mysticism, it is quantum mechanics. The entanglement is real, even though it is completely inaccessible in practice. The information is genuinely there, even though no conceivable instrument could read it. The conservation is exact, even though we can never verify it at the level of individual quantum states of macroscopic objects. It is a consequence of the mathematical structure of the physical world, as fundamental and as unavoidable as the conservation of energy or the quantization of angular momentum. The fundamental laws of physics, including quantum mechanics with its principle of unitary evolution, including general relativity with its laws of black hole thermodynamics, including thermodynamics itself with its first law of conservation, all point in the same direction. Information, the complete quantum description of physical reality, is conserved. It is never created from nothing and never destroyed into nothing. It transforms, disperses, scrambles beyond any conceivable practical recovery, but it persists. That persistence is not a minor detail or a theoretical curiosity. It is the universe's deepest structural commitment, the one feature of physical law that runs through every framework we have, from the simplest classical mechanics to the most exotic reaches of quantum gravity. Think about what that actually means in the most immediate and personal terms. Every interaction you have ever had with the physical world has left a mark. Every photon your eyes have absorbed, every breath of air you have inhaled and exhaled, every surface you have touched, every word you have spoken that has set air molecules vibrating in patterns that propagated outward as sound waves and scattered off every surface in a room. All of it has altered the quantum state of the environment in ways that are, in principle, encoded and preserved. You have been modifying the quantum state of the universe in ways that can never be undone since the first cell in your body formed. And the universe has absorbed all of it, kept all of it, entangled all of it into its ongoing quantum state, carrying the record forward with perfect fidelity into every moment that follows. The wood in the fire is not gone. The person who lived and thought and felt and then died is not gone from the universe. Not in the sense that the physical information that constituted them has ceased to exist. That information has dispersed into the environment, scrambled into the vast quantum state of the surrounding world, entangled with billions of other particles, impossible to recover, inaccessible in any practical sense. But conserved, present, encoded in the fabric of a reality that does not discard what it has held. The stars that burned and collapsed billions of years before our solar system formed are not gone. Their light still travels outward through the universe, some of it still carrying the spectral fingerprints of elements forged in their cores. Their material became the gas clouds that gravity gathered into new stellar nurseries, from which new generations of stars formed, around some of which planets condensed, and on at least one of which life emerged, and in at least one product of that life this very thought is being expressed. The information of those ancient stars is not gone. It is here. You are part of it. The matter and energy and information of everything that has ever existed in the observable universe is still, in some form, somewhere, present. The universe is, in the deepest physical sense, a closed system, and closed systems do not lose what they contain. They rearrange it, endlessly, ceaselessly, without beginning or end, with perfect fidelity to the conservation laws that are the universe's deepest commitments. There is something in this that is both comforting and vertiginous. Comforting because it means that nothing is ever simply gone, that the universe does not discard its history, that in some physical sense the past remains real and present, encoded in the now. Vertiginous because it means that the present moment is not the clean, unencumbered. Now we experience it as, but rather the accumulated, compacted, infinitely scrambled record of everything that has ever happened. and we are embedded in it, made of it, carrying it forward into the future as part of the endless transformation of what the universe has always been. And there is one more layer of strangeness that I want to leave you with, one that emerges when you combine the conservation of information with the quantum nature of matter and the holographic encoding of space-time. If all the information about the history of the universe is encoded in its current quantum state, and if you are part of that quantum state, then in a very precise mathematical sense, the information about everything that has ever happened is, in some form, distributed through you. You're not just made of stardust in the poetic sense. You're made of the quantum state of particles that have been interacting and entangling and scattering for nearly 14 billion years, carrying in their correlations and superpositions the scrambled, unreadable, but physically present record of cosmic history. Your atoms were forged in stellar interiors. Your heavier elements were scattered by supernovae. Some of your hydrogen was there at the Big Bang. The photons that your eyes detect have been travelling through space for seconds or billions of years. The neutrinos passing through your body right now are relics of the early universe and of every supernova that has ever occurred. You're not separate from the information that the universe preserves. You are part of it, a local pattern in it, a temporary structure through which it flows and in which it is momentarily organized into something capable of looking outward and asking, in genuine bewilderment and awe, what everything is made of and where it all goes. And there is something extraordinary embedded in this particular fact, the fact that you are asking. Because the conservation of information does not just apply to matter and energy in the passive sense. It applies to the information content of the physical substrate of cognition itself. The pattern of electrochemical activity that constitutes a thought in a human brain is a physical process, subject to the same conservation laws as every other physical process. The specific arrangement of synaptic connections that stores a memory, the precise pattern of ionic gradients and neurotransmitter concentrations that constitute a moment of conscious experience, these are physical configurations of matter and energy, and as such they are subject to the same physics we have been discussing. When a person dies, and the physical processes of life cease, the information that constituted their unique neural pattern does not simply vanish. It disperses, as all information does, into the surrounding environment, scrambled into the thermal motion of molecules and the chemical reactions of decomposition and the subtle quantum states of everything the body touches and breathes and radiates into. It becomes, in the language of quantum information, hopelessly scrambled. It can never be reconstructed, not by any conceivable physical process operating under the laws of physics as we know them. But it is there, in the collective quantum state of the world, in the finest grained correlations between particles that will never be measured with sufficient precision to read it, preserved with the same implacable conservation that preserves the information in burned books and collapsed stars. This is not a comfort exactly. It is more unsettling than it is reassuring, because it means something strange and hard to fully absorb about the nature of endings. The ending of a conscious mind, the cessation of thought, the disappearance of a perspective, is as real and as irreversible as it feels. The scrambling is complete, the practical loss absolute. But at the level of fundamental physics, the information that constituted that mind, that collection of particular quantum states and correlations, is still present in the universe, encoded in forms no one will ever read. Whether that fact carries any meaning beyond the strictly physical is a question physics cannot answer. But it cannot help raising it. Physics is very good at describing the world in terms of information, energy, and geometry. It is not equipped to tell us whether there is significance to the conservation of information beyond the mathematical fact of it. That is a question for philosophy, for theology, for the full range of human inquiry into meaning and value. But what physics can tell us, and what we've been exploring throughout this journey, is that the universe takes extraordinary care of its quantum states. The laws of nature are, in a deep technical sense, laws of conservation, and the most fundamental thing they conserve is not matter, not energy, but information. And the answer, the genuinely unsettling, cosmically strange, and somehow deeply meaningful answer that physics keeps giving us, is that it does not go anywhere. It is here. It has always been here. It will always be here, in forms that shift and transform beyond recognition, across timescales that dwarf the present age of the universe, across landscapes of geometry and entanglement that our current theories can only begin to map. Nothing ever truly disappears. Think about what that actually means for the universe you live in. The light from the first stars, stars that burned for perhaps a few 100 million years and then collapsed billions of years before our solar system existed, has been travelling through the universe ever since. Some of it has been redshifted by the cosmic expansion until it falls below any frequency we can detect, but it is still there, carrying its information, its spectral fingerprint of the elements those stars were made of. The gravitational waves from the first merging black holes and neutron stars, ripples in the fabric of space-time itself, are still propagating outward, long since dispersed below any instrument we have ever built or will ever build to detect, but physically present, carrying their encoded history. The cosmic microwave background, the faint thermal glow that pervades all of space in every direction, is the red-shifted afterglow of the Big Bang. The remnant radiation from when the universe was about 380,000 years old and matter and radiation first decoupled. Every photon in that background carries information about the density fluctuations in the early universe, information that has been encoded in the pattern of temperature variations across the sky, information that tells us about conditions in the universe when it was a small fraction of its current age. We can read this information. We have read it with extraordinary precision, using telescopes and satellite observatories. The universe has been patient enough to preserve it for us across 13.5 billion years, and deeper still, encoded in the statistical correlations between those ancient photons, is information about quantum fluctuations that occurred during cosmic inflation in the first tiny fraction of a second of the universe's existence, at energy scales so extreme that they go beyond the reach of any particle accelerator we could ever build. Those quantum fluctuations were stretched and amplified by the inflationary expansion into the density variations that seeded all the structure we see in the cosmos, every galaxy, every star, every planet, every atom in your body, ultimately traceable back to the quantum noise of the very early universe. And that noise, those fluctuations, are still encoded in the universe today, in the patterns of the cosmic microwave background and the large-scale structure of galaxy distributions. The universe is legible for those who know the language. This is what I want to leave you with, not just the abstract principle that information is conserved, but the concrete reality of it. The universe preserves its history in readable form, encoded in radiation and structure and quantum correlations, across timescales and at energy scales that our instruments are only beginning to probe. We have barely started to read the archive. The pages go back almost 14 billion years, and they are still there. This is the universe we live in, not a universe that wastes and forgets and moves on, but one that preserves, transforms, encodes, and carries everything that has ever been into everything that will ever be. The physics is clear on this, even where the mechanisms remain mysterious and the deepest theoretical questions remain open. The books balance. They have always balanced. They always will. And somewhere in that perfect accounting, in the flawless conservation of information from the first quantum fluctuation to the last photon dispersing in the heat death and beyond, is the universe's answer to our deepest question about endings. There are none. Not at the fundamental level. Not in the language of the laws of physics. There is only transformation, only the endless, relentless, magnificent rearrangement of what has always been present into forms we could never have predicted, carrying meanings we may never fully read. We began this journey with a campfire, with the deceptively simple question of where the wood goes. We end it at the edge of quantum gravity and the deep future of the cosmos, where the same answer echoes across every scale. It does not go away. It transforms. The universe keeps it. The universe keeps everything. And this is, in the end, the deepest reason the title of this exploration should give you pause. Because we are not just talking about a dry conservation theorem, a bookkeeping rule for physicists to satisfy themselves that their equations are consistent. We're talking about something that, if true, changes the fundamental picture of what existence means. In a universe that conserves information, nothing is ever truly finished. Nothing is ever truly over. Every moment that has ever been is still present in the structure of reality, encoded in the correlations between particles, written in the geometry of space-time, preserved in the quantum state that carries everything forward. The stars that burned before our solar system existed, the civilizations that rose and fell before writing was invented, the species that lived and went extinct before anything witnessed them, the photons from galaxies so distant their light began its journey before the Earth existed, All of it is still there, archived in the quantum state of a universe that does not forget, not accessible, not recoverable, not readable by any instrument we have or ever could have, but present, real, conserved. That should disturb you, or at the very least unsettle you in the way that the most truthful things tend to do. Not because it is frightening, but because it quietly and completely dismantles the assumption that things end. They do not end. They transform and disperse and become inaccessible, which feels like ending from the inside. But from the perspective of the fundamental laws that govern every particle and field in existence, there are no endings. There is only the endless, perfectly conserved, endlessly transforming record of everything that has been. This is Deep Space Intelligence, and I am Liam. Thank you for watching, and for thinking, and for being part of the universe that is asking these questions about itself.